Hello everyone, welcome to the Let's Learn YouTube channel. So in today's class we will be talking about ethers. Okay, so ethers is the topic of our discussion. So the flowchart for today's class is, first we speak generally about ethers, then we will get into the preparation of ethers, and then we'll study the physical and chemical properties of ethers. Alright, so we all know ethers have structural formula ROR, isn't it? It need not be only R, it can be aryl group also, isn't it? It can be aryl group also. So based on these R groups, we can classify aryl ethers or alkyl ethers, generally ethers, into two categories. What are they? They can be symmetrical ethers or they can be unsymmetrical ethers. These unsymmetrical ethers are also called as mixed ethers. Mixed ethers. Okay. So what does it mean? That means in symmetrical ethers, what do we have? We have both R groups would be same. That means ROR. So this R group is exactly same. But in the case of unsymmetrical ethers or mixed ethers, what do we have? We have different alkyl groups or aryl groups on the either side of the oxygen. So that's the only difference between symmetrical and unsymmetrical ethers. So this is the general discussion about ethers. Now if I talk about the structure or shape, okay, let us talk about shape of ethers. So ethers have bent shape. So the way water has bent shape, we all know this is around 105 degrees Celsius, 105 degrees, isn't it? Similarly, ethers also have bent shape. So if this is oxygen, this is R group, this is R group. Since in water we have hydrogen atoms, okay, so there is not much steric repulsion, isn't it? But in the case of ethers, these R groups are little bulky when compared to hydrogen. So that's why the bond angle is much larger. The bond angle is more when compared to water. So here the bond angle is 110 degrees. Okay, here it is only 105 because there we have only hydrogen atoms. But here in ethers, these hydrogen atoms are replaced by alkyl groups. So because of the bulkiness of these alkyl groups, there is some steric repulsion. So because of the steric repulsion, they go away so that bond angle increases. So the approximate bond angle is 110 degrees in case of ethers. Alright. So this is all about general discussion of ethers. Now let us talk about preparation of ethers. What are the different ways to prepare ethers? So we are talking about preparation of ethers. So first, there are two main methods to prepare ethers. One is from alkyl halides, the other is from alkyl alcohols. Okay. So first let us talk about alkyl halides. How can we synthesize ether from alkyl halide? Okay. So the first one is Williamson synthesis. So this we have already known, isn't it? Williamson's synthesis. So what happens in Williamson synthesis? What are the reagents required? That is sodium alkoxide, isn't it? So first we take sodium alkoxide, that is RONA, and this sodium alkoxide, when it reacts with alkyl halide, okay, let it be R dash, okay. So when sodium alkoxide reacts with sodium alkyl halide, I repeat, sodium alkoxide, this is sodium alkoxide. So when this sodium alkoxide reacts with alkyl halide, so what happens? We see the formation of ether, that is ROR dash. One R from here, one R from the R dash from here. So we have the formation of ether along the byproduct NaX. So this is the Williamson synthesis. There are some important points to be kept in mind in the case of Williamson synthesis. What are they? This reaction proceeds through SN2 mechanism. Okay, SN2 mechanism. That means there is no cation carbocation formation, there is no carbocation intermediate. The attack of the nucleophile and the leaving of the leaving group both happen at the same time, isn't it? So we have also seen in the case of SN2 reaction, primary undergoes primary alkyl halide goes undergoes reaction fast, isn't it? So tertiary, secondary, primary, out of primary, secondary, and tertiary, primary undergoes fast reaction in SN2 case, then covered by then secondary, then tertiary, isn't it? So this is how. So always remember, in SN2 mechanism, primary alkyl halides will undergo fast reaction. Now suppose if we have different primary alkyl halides, so let me write like this: the order of reactivity in different primary halides, in different primary halides. So we have different primary halides like CH3X, CH3CH2X, CH3CH2CH2X, and so on. So when the bulkiness increases, like when the alkyl groups increases, the reactivity decreases. So always remember, when the number of carbon chains, when the carbon length of the carbon chain increases, the reactivity of alkyl halide decreases in Williamson synthesis. And one more important thing is the order of reactivity. The order of reactivity is primary alkyl halide undergoes fast reaction when compared to secondary alkyl halide and when compared to tertiary alkyl halide. Why is that? Why? Because tertiary alkyl halide always prefers elimination product, prefers elimination, isn't it? That means it forms, instead of forming alcohol, instead of forming ethers, it forms alkene. Okay, so the order of elimination, order of elimination is tertiary, secondary, primary. So these are the some general factors you have to keep in mind when we are talking about Williamson synthesis. No, not this is not all. So there are some restrictions or drawbacks with this Williamson's reaction. What are they? Let us see. Let me write note here. See, the first one is aryl bromides, aryl halides. Let me write aryl halides cannot be used to make ethers. What does it mean? That means if I have this phenyl bromide and if I add sodium methoxide, then what we are supposed to get? We are supposed to get CH3O C6H5. But this is not possible. Why? Why? Because aryl halide cannot undergo this reaction. Why is that? Here we have bromine in on the benzene ring. So when the bromine is on the benzene ring, it will also show plus R effect. Because of that, there is partial double bond character between bromine and carbon atom. Okay. So because of this, it doesn't undergo SN2 reaction. That's why we'll write no reaction. No reaction is possible. And as a consequence of this, there is one more point, that is diaryl ethers. What is that? Diaryl ethers are also not possible. Are also not possible. Why? Same reason. Same reason. So if I take alkyl bromine along with phenoxide ion, then what we are supposed to get? We are supposed to get this one, isn't it? So let me draw this properly. So we are supposed to get this one, this product, this ether, but this is also not possible. Why? Same reason, phenyl bromide cannot be used. So here we can write no reaction. Okay, So this is all about Williamson synthesis. So these are some important points which need to be kept in mind. Okay, so till now we have done the first method of preparation of ether. Now let us talk about second method of ether. What is that? So let me write B. That is from dry Ag2O, that is silver oxide. In the preparation of alcohols, we have seen when alkyl halide reacts with moist Ag2O, moist, this is important. There we have seen the formation of alcohol, but here we are talking about dry Ag2O. Okay, dry Ag2O. So this is important. Here moist, but here we are talking about dry. So this is important. So when alkyl halide reacts with dry Ag2O, what are we expecting in the presence of heat? We get ROR, that is ether formation along with silver halide. So this is the one of the important methods to make ethers from alkyl halides. So till now we have discussed two methods, and that those two both methods are from alkyl halides, that is preparation of ethers from alkyl halides. Now let us talk about preparation of ethers from alcohols, that is from alcohols. So first one is by dehydration. By dehydration. So when we have alcohol, for example, if I have CH3CH2OH ethanol, if it undergoes dehydration in the presence of concentrated H2SO4, and okay, let me write like this. So it undergoes dehydration in the presence of concentrated H2SO4. Then what do we get? We get ether. Okay, CH2CH3. Very good. Same reaction will happen if I take Al2O3, that is aluminum oxide, at 250 degrees Celsius. Temperature is important. Okay, this is 250 degrees Celsius, this is 140 degrees Celsius. So ethanol, when it undergoes dehydration at 140 degrees, it forms ether. Similarly, CH3 ethanol under the presence of Al2O3 undergoes dehydration and forms same ether, that is CH3CH2O, CH2CH3. Okay, now here comes a very important point. If I slightly alter the temperature to 170 degrees Celsius, then we get alkene, that is elimination product. Okay, this is important. So that's why the temperature is very important in this particular reaction. Why? If it is 140 degrees, we are getting ether, but if it is 170 degrees, we are getting alkene. Same here also. If we change the temperature from 250 degrees to 350 degrees, then I get alkene elimination. So at higher temperatures, alkene elimination products are more possible. So this is how we generate ethers. This is how we prepare ethers from alcohols. Okay, so the one more thing you have to keep in mind is, in order to prepare ethers, in the preparation of ethers, so in the preparation of ethers, we take, or we have to take alcohol in excess. Okay, so from alcohols, this is how we synthesize ethers. So this is the first method. Now let us go to the second method, that is by the action of diazomethane on alcohol. Okay, so by the action of diazomethane and alcohol, we can synthesize ether. Let us see how. So the first important thing in this reaction is catalyst. So we take some Lewis acid catalyst, for example BF3 or HBF4. Okay, so any one of them can be taken as an catalyst. So the general reaction for this reaction is when we have alcohol and when it combines with diazomethane. What is its formula? CH2N2. Okay. So the formula for diazomethane. So let me write here. Diazomethane is alcohol CH2N2. So when alcohol combines with diazomethane, what do we get? We get ether. Okay, along with nitrogen. So this is the reaction of diazomethane and alcohol. So from alcohols we can synthesize again ether using diazomethane or as well as dehydration. Now let's talk about the third method to prepare ethers. What is that? Addition of alcohol to alkenes. So if I take alkene here, okay, if I take alkene and if I add alcohol, then what happens in the presence of H2SO4? So OH will add to one side, OR will add, sorry, OR will add to one side of the carbon and OH will add to the another side. So we have CC H here, OR here. So why I am writing OR only on that side? No, it can be written on any carbon. Why? Because these are symmetrical alkenes. So the mechanism passes through carbocation formation. So this mechanism, this reaction proceeds through carbocation formation. Carbocation formation. So when does the carbocation form? When it undergoes SN1 reaction. So the mechanism here is SN1. So it is forming carbocation here. So when we have the carbocation formation, carbocation is, so all this is fine in the case of symmetrical alkenes. OR can be added any side. But what about unsymmetrical alkenes? Then there comes Markovnikov rules, isn't it? So since it is passing through carbocation formation, so here also we apply the Markovnikov rule to identify the final product. Yes. So this is the final method to prepare ether from alcohols. So till now we have seen 5 methods to prepare ethers. What are they? So the first method is from Williamson synthesis, and the second method is using dry Ag2O, that is silver oxide, and the third method is through dehydration of alcohol. Fourth method is action of diazomethane on alcohol, and the fifth method is addition of alcohols to alkenes. Alright, I hope no issues till now. Yes, so we are done with the preparation of ethers. Now let us study the physical properties of ethers. What are we studying? We are studying physical properties of ethers. Yes. See, when we study physical properties, first we see the structure and we understand its structure properties, isn't it? So this RO bond, that is polar. Okay, because here it is carbon oxygen bond, isn't it? So this is polar bond because there is some electronic difference between carbon and oxygen. So ethers have polar bond. CO bond in ether, so let me write like this, is a polar bond, and hence ether possess a net dipole moment. Ether possess a net dipole moment even if they are symmetrical. This is important. Even if they are symmetrical, that means if I have CH3 OCH3, they're symmetrical, isn't it? Because on either side of oxygen we have same alkyl group. So when they're symmetrical, how does it work? Why is this either polar? So we have CH3 O CH3. So if I talk about polarity of this bond, it is this towards this side. and here it is towards this side. So both should cancel, right? But still, why this compound has net dipole moment? Anyone? Yes, very good. Because of its shape. It has bent shape, right? So because of this direction, here we have like this. Here the polarity has this direction. So in total, at the net, finally we have net dipole moment in this direction. So because of this shape, the symmetrical ethers also possess net dipole moment. So that's why it is important. So if I give some values, let me give some examples. So for this, mu is 1.3 dBi, and if I have C2H5O C2H5, here mu is 1.18 dBi. Okay, so even if ether is symmetrical, even then it has some net dipole moment. That is important. Now let us compare these ethers with all alcohols. So first comparison is boiling point. Always remember, boiling point of ethers is always less than boiling point of alcohols. Why? Why is that? See, alcohol, sorry, ether has ROR structure, isn't it? So no hydrogen bonding is possible here. So no hydrogen bonding is possible, isn't it? Why is that? Because there is no hydrogen on the oxygen atom. For example, if I talk about alcohol, so because of the electronegative difference, there is partial positive charge and hydrogen, and this hydrogen forms hydrogen bonding with oxygen of other alcohol molecule. So when there is, for hydrogen bonding to exist, there should be hydrogen on the electronegative atom, that is oxygen here. But in the case of ethers, there is no hydrogen on the oxygen, which is electronegative atom. So no hydrogen bonding possible. Since there is no hydrogen bonding possible, the boiling point is less when compared to alcohols, because in alcohols intermolecular hydrogen bonding is possible, but in ethers it is not the case. So low boiling point when compared to alcohols. And next property to compare between ethers and alcohols is solubility. Solubility of ethers in H2O. See, both ethers and alcohols have similar solubility, have similar solubility solubility in water. Why is that? This is because of hydrogen bonding formation. This is due to hydrogen bonding. Just now I said hydrogen bonding is not possible, but how come here it is possible? Wait, let me tell. So if it is ether, and when it is dissolved in water, so what is the structure of water? What is the formula of water? H2O. So OH2. Now there can be hydrogen bonding possible between this oxygen and this hydrogen, isn't it? Same goes here also. So when we add water to the ether, because there are hydrogens on the water molecule, so hydrogen bonding is possible. As a result of this, the solubilities of ether is comparable to the solubilities of alcohol in water. Alright. So these are the important physical properties of ethers. With this we conclude the physical properties of ether section. Now let us talk about chemical properties of ether. What is that? It is chemical properties of ethers. See, we study the chemical properties under three phases or three parts. First one, see, ROR. First we study those reactions which involve this oxygen. This is called ethereal oxygen. That means the oxygen which is a part of ether, ethereal oxygen. Okay, so we'll see those reactions which involve this oxygen. Next we see the cleavage of this ROR bond. Okay, next we'll see the cleavage of ROR bond. So that's all about it. And the third case we'll see the reaction of these alkyl groups of ether. So in the first case we study those reactions which involve the this oxygen, and in the second case we study those reactions which involve the this RO bond breakage, and in the third case we study those reactions which involve these alkyl groups. Okay, so that's all about it. Let me start with ethereal reactions of ethereal oxygen, ether's oxygen, that means oxygen of ether. So before starting, please remember that ethers are quite stable. Okay, their reactivity is very less when compared to other functional groups like alcohol. So here we can write ethers are quite inert and stable compounds. Okay, stable compounds. So they require drastic conditions or some special conditions to make them react. Okay, so some reactions are possible, let us study them. So first one is reactions of etherical ethereal okay ethereal oxygen. What is it? Ethereal oxygen, that means the oxygen which is present in ether functional group. So first one is action of air. Action of air, that means what happens when ethers are exposed to air. So I have ether here. When it is exposed to air, the oxygen the oxygen which is present in air attacks this ether. As a result of this we get peroxide. So suppose if I take CH3 CH2 here, or CH2 CH3 here, now what happens? As a result of this oxidation it forms peroxide. Okay, always remember ethers when exposed to air form peroxides, and these peroxides are very explosive. Peroxides are very explosive. So it is very dangerous to expose ethers to air. So to always check whether to always check whether we have to always check whether the ether is already exposed or not. How do we check that? For test for peroxides. So with a small test for peroxide, what is it? So if I add Fe2 plus ion to a peroxide, okay, peroxides are oxidizing agent. So when we add Fe2 plus, it undergoes oxidation to form Fe3 plus. Now to this, if I add potassium thiocyanate, okay, if I add potassium thiocyanate, what happens? It forms complex. This is FeCNS thrice. It forms complex, and this complex has red blood color. It has red blood color. So whenever, in case if we have doubt that whether ether is exposed to air or not, so we always check the peroxide test. We always go for peroxide test. If there is peroxide, if the ether is exposed to air, then we'll have the red color formation, red blood color formation. Okay, so this is the first reaction of ether which involves ethereal oxygen. Okay, so this is all about first reaction. Now let us talk about second reaction. What is it? Second reaction is action with concentrated acids. Okay, see, we have ether, and this ether has got some lone pairs, isn't it? This ether has got, the oxygen has got lone pair. So because of this lone pair, it can donate that lone pair, isn't it? It can abstract the proton with that lone pair. So as a result of this, these ethers will act as Lewis bases. Okay, so ethers act as Lewis bases already. So when it is combined with concentrated H2SO4, now what happens? It acts as a Lewis base, and this base abstracts proton from this sulfuric acid. So as a result, we have the formation of salt here. So this is R O R. Since it is abstracting proton, it will get this positive charge and the remaining anion. So this is the salt we get when ethers react with concentrated acids. So this is the second reaction. Now let us talk about third reaction, that is reaction of ethers with Lewis acids. So just now I said ethers act as Lewis base, so they can react with Lewis acids. What are Lewis acids? Lewis acids are those which are electron withdrawing, electron receiving, which can receive electron pair, isn't it? So when we have Lewis acids like BF3, they can take extra electron pair of this ether oxygen and form complex. So let me write here, being Lewis acids, ethers form coordination complexes with Lewis acids such as BF3, AlCl3, etc. So for example, if I have this ether, okay, now when it combines with BF3, what happens? It forms a complex. What kind of complex? Let us see. So the lone pair, it donates, it forms a coordination compound with this BF3. Okay, with this BF3. So this complex is called boron trifluoride ethyrates. See, always remember when Lewis acids, so they're like, when ethers combine with Lewis acids, they form ethyrates. What is that? Let me write spelling here. Ethyrates. So this is important. So if we see one, practical example, with Grignard reagent. So suppose we have 2R2O ether. When it combines with RMGX, that is Grignard reagent, we have the formation of again complex. So RMGX, and here these ether groups are associated through coordinate bond. So this is called Grignard reagent Grignard reagent etherate. So that means ethers can form etherate complexes when they combine with Lewis acids. So here RMGX is a Lewis acid. It, so that's why it forms etherate complex with. As a result of this, whenever we have RMGX, that is Grignard reagent in a reaction, you always see there is ether written on the arrow, isn't it? Why is that? Because of this complex only. Since RMGX can form complex with these ethers, it is easily soluble in ether. Okay, that's why you always take RMGX with ether, so that RMGX is soluble in ether. So this is all about reaction of ethers with Lewis acids. Now let us talk about the fourth reaction. What is the fourth reaction? Oxidation. Oxidation with potassium dichromate, that is K2Cr2O7 in the acidic medium. See, always remember, those ethers which have alpha hydrogen can undergo oxidation. So only those ethers which have alpha hydrogen can undergo oxidation. What does it mean? For example, CH3 CH2O CH3. Okay, so here this is the functional group oxygen, and the carbon next to this oxygen is alpha carbon. So whatever hydrogen present on the alpha carbon will act as alpha hydrogen, isn't it? So all those alpha hydrogens, so wherever we have alpha hydrogens, they all can go oxidation reaction with K2Cr2O7 in the presence of H plus. And just one more thing, please keep in mind, if there are two alpha hydrogens available, two alpha hydrogens, then we have the formation of carboxylic acid. Let us see the example, okay? And if there is only one alpha hydrogen in the ether, then we have the formation of ketone, okay? Let me demonstrate with an example. For example, if we have this ether, okay, unsymmetrical ether, so when it undergoes oxidation in the presence of acidic medium, what do we get? We get CH3COOH, that is from this side chain, to CH3CH2COOH. From this alkyl chain we get this acid. See, I'm getting carboxylic acids because I have two alpha hydrogens on the alpha carbon. If I have only one alpha hydrogen, like now what happens? The same reagent, under the presence of same reagent, what do we get? We get CH3COOH from this side, and here we get simply ketone, because there is only one alpha hydrogen here. If there had been two alpha hydrogens, then we can find the formation of carboxylic acid product. But since we have only one alpha hydrogen, it undergoes reaction to form ketone. Okay, so this is all about oxidation with K2Cr2O7 in the presence of H plus. So till now we are talking about reactions, those reactions which involve ethereal oxygen. So we have studied 4 reactions under this heading. Now let us study those reactions which involve cleavage of CO bond. So it is reactions involving cleavage of CO bond. Okay, reactions involving cleavage of CO bond. So what is that? So first one is cleavage by, so let me change my pen. First one is cleavage by halogen acids. So when we have ether, when we add halogen acid at 373 Kelvin, I repeat, at 373 Kelvin, what do we get? We get alcohol along with alkyl halide. So one R forms alcohol, another R forms alkyl halide. Now, if we take alkyl halide in excess with same reaction conditions, then we see the formation of only alkyl halides, no alcohol. Please remember that. Okay. So if we take excess of alkyl halide, then we'll have the formation of only alkyl halide. Why is that? Why? Because with whatever alcohol forms in the first step, it still undergoes reaction with extra halogen acid and form Rx. Okay, that's why to synthesize Rx only, we need to have Hx in excess. For example, if I have this ether and if I react with 2Hi, that is excess. Okay, because of excess, then what do I get? I get 1 2 3 4 carbons. So okay, don't think it as a radical. So we have 4 carbons, so it is CH2 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 I. Okay, we get alkyl halide. All clear till now? Very good. Now suppose if we have unsymmetrical alkenes, see, when we have symmetrical alkenes, doesn't matter which forms alcohol, which forms alkyl halide. But what if we have unsymmetrical alkenes? So right here, in the case of unsymmetrical ethers, So if we have unsymmetrical ethers, so that small, so alkyl halide is formed on that alkyl group which is smaller in size. So in case of unsymmetrical ethers, the site of cleavage, the site of cleavage is such that the halide is formed from the alkyl group, from the alkyl group which is smaller in size. So for example, if I have like this ether, and if I add iodine, sorry, halogen acid, then what do I get? I get CH3I along with C2H5OH. Okay, so this is what I meant. So iodine, that alkyl halide forms in which alkyl group is smaller. So again, if I take one more example, so and if I add the same reagent, then what do I get? I again get CH3I along with alcohol, secondary alcohol. Okay, now in case if we have one of the side chain is tertiary, I repeat, if one of the alkyl group is tertiary, if one of the alkyl group is tertiary, then that that alkyl group forms alkyl halide. Okay, then alkyl halide is formed from the tertiary alkyl group. Okay, so if we see the example, for example, if I take this example which is tertiary ether, now if I add Hi at 373 Kelvin, then what do I have? I have tertiary alkyl halide along with methanol. Okay, this is what I meant. So always remember, if we have tertiary alkyl chain, then tertiary alkyl halide will be formed from the ether in the presence of halogen acid. Apart from these alkyl side chains, if we talk about aryl halides, okay, if we talk about alkyl aryl ethers, give always give phenol and a molecule of alkyl halide. What does it mean? That means if we have alkyl aryl ether, so on one side of carbon, instead of R group, if we have aryl group, and on other side if we have methyl group instead of alkyl group. Okay, so when this undergoes this reaction at 373 Kelvin, then always remember, we always get phenol only. Now if I have benzyl ether, sorry, okay, in case of benzol alkyl ether, benzyl alkyl ether, so then what do we have there? For example, we have CH2O CH3. When this undergoes the same reaction, we get CH2I with CH3OH. Okay, yes. So this is all about reaction of halogen acid with ether. And one more thing to keep in mind is the order of reactivity in different halogen acids. So the order of reactivity is HI, HBr, HCl, HI. Okay, so this is all about the react cleavage of halogen acid. Now another reaction is, let us talk about another reaction, that is reaction of reaction with PCl5. What happens when PCl5 reacts with ether? So I have ROR, and in the, if I add PCl5 and heat it, okay, I get alkyl halide, okay, along with POCl3.